Kia ora koutou katoa. Welcome to the NZ seminar, the online NZ seminar. We're going to jump straight into the presentation today. Today, our seminar is going to be, their seminar, it's going to be on seismic design observations from a study tour of Chilean-based isolation hospitals. We're going to hear from 5 different speakers. The first speaker is going to be Quincy from University of Auckland, then Dion from Becca Erickson from Campus of Engineering, then Jeff from University of Canterbury, Mark from Holmes, and last but not least, Jan from WSP. I'm going to hand over to Quincy straight away. Very quick presentation. Introduction, sorry. Over to you, Quincy. Thank you.
Great. Thanks, Catalina. Good morning, everyone. My name is Quincy from the University of Auckland. In this presentation, we'll be sharing some of our observation during a 5-day technical visit to Chile in April earlier this year. This was conducted as part of a project looking to share experience and knowledge on constructing earthquake-resilient hospitals between our 2 countries, with a focus on connecting our practicing engineers. So in case we run out of time at the end, I'd like to just first acknowledge the funders of the project, Royal Society of New Zealand and MBIE, without which this project would not have been possible. And also I'd like to acknowledge our list of very well-known and influential Chilean hosts, which has made our visit so productive and enjoyable. So the plan of attack for this presentation is for each of us to take you through 1 or more buildings that we visited, highlighting some of the notable features as we go. And then hopefully by the end, you may notice a theme or at least something that you can take back to your day-to-day practice. So why this project in collaboration with Chile? Well, in terms of earthquake engineering research, Chile and New Zealand are natural partners on both sides of the Pacific Ring of Fire. We both rest on the active subduction zone, and we both have a very long history of designing for destructive earthquake. And just an indication for relative seismicity, if you're not sure, between the 2 countries, as a rough rule of thumb, New Zealand has a magnitude 6 earthquake every year, a magnitude 7 every 10 years, and a magnitude 8 every 100 years, while Chile has a magnitude 6 earthquake every 6 weeks, a magnitude 7 every 3 years, and a magnitude 8 every 10 years. So as you can see, Chile really is a living laboratory for earthquake engineering. So another reason that we embarked on this project is that both New Zealand and Chile suffered a major earthquake around 2010. Well, for New Zealand, the 2011 Christchurch earthquake and the 2010 magnitude 8.8 Morlaix earthquake in Chile. These earthquakes caused widespread devastation in our respective country, and in particular for Chile, many of their hospitals had to be rebuilt. So this coincidental timing really put us on a parallel recovery timeline, which allowed for some very interesting comparison studies. So what you see is that our project on seismic performance of hospital is particularly timely. Chile has been actively constructing new hospital in the past 10 years. They have recently completed 25 large-scale base isolated hospital, and I think they have at least 25 more to complete. And this is happening while New Zealand is going through a significant investment in expanding and renewing our own healthcare infrastructure as well. So according to government's sort of recently release, there are 67 major projects in flight worth a total of 6.4 billion New Zealand dollars. This kind of presents us with an incredible opportunity to learn from Chile's experience, which is roughly 5 to 10 years ahead of us, and potentially giving us a shortcut to some of the success and bypassing some of the mistakes. So Chile is a very long and skinny country, and our group selected 2 cities to visit, Santiago in the middle of the country and Alto Hospicio near Iquique up north. The 2 cities are about sort of 1,500 kilometers apart, and that's roughly the distance between Auckland to Queenstown. So due to that distance, the 2 cities have very different climates and outlook. Santiago, the capital, has a population of approximately 7 million with 39 hospitals in the region. It's a more temperate region, while Iquique is essentially a desert town and a very hostile environment. Chile divides itself into 3 seismic zones for design, 1 to 3, 1 being the lowest, 3 being the highest. Santiago is in the seismic zone 2, and Iquique is located in seismic zone 3. Overall, Santiago seismicity is similar to Wellington, and Iquique is quite a bit higher than that. So for the 5 days, We had a very hectic schedule in Chile. On the first day, we visited the military hospital, which was their first ever base isolated hospital in Chile, constructed in 2009, just before their 2010 earthquake. We also visited the base isolated Baha'i temple and had a workshop in the University of Chile in the center of town on the first day. On day two, we visited two hospitals under construction, including Sotero del Río, which will be the largest hospital in Chile. On day three, we visited a operating hospital, which is base isolated and Visistamba. And then on day four, we traveled to Iquique and visited Chile's first friction slider base isolated hospital. And then we returned to Santiago for a closing meeting. And with that, I'm going to pass it on to Dion.
Thanks, Quincy. So I'm going to speak to two of the base isolated hospitals that we visited, the first of which is as Quincy mentioned, the Military Hospital of Santiago. So this was Chile's first base isolated hospital, designed in 2001 and constructed over a 3 to 4 year period, 2006 to 2009. The hospital itself actually comprises of two separate structures. It comprises of a fixed base non-isolated wing, which houses the outpatients and visitors, and an isolated central building which accommodates the ICU, theatres, medical equipment, etc. So it was a unique site in which to observe the performance of these two buildings following the 2010 Mole earthquake. The isolated building comprises of 164 high damp rubber bearings, and the structural system itself is a concrete moment frame superstructure. So as Quincy mentioned, the site or this building experienced the 2010 magnitude 8.8 Mole earthquake. The epicenter was about 200 kilometers from this hospital, with a PGA at the site of about 0.22 G. And as I mentioned, it represented a unique opportunity to observe the performance of a fixed base and an isolated hospital at the same site. Both buildings were operational after the earthquake, though the fixed base wing suffered moderate non-structural damage, which impacted its ability to remain fully functional after the event. So the damage generally consisted of partition damage, damage to elevators, and one of which the counterweight actually detached from the elevator. And in fact, dust from the ceiling spaces actually triggered the fire alarms and the evacuation warnings throughout that structure. Well, in contrast, the isolated structure essentially remained fully operational immediately after the earthquake. Sorry, just having trouble. Here we go. So being the first base isolated hospital, it received quite a lot of attention during design and construction. I'll just run through some of those aspects now. So the bearings themselves were high damp rubber bearings. Interestingly, high damp rubber bearings are no longer permitted in Chile due to the age effects of high damp rubber bearings hardening over time. Every bearing contained active and passive fire protection. It's probably a little bit hard to see from this image here, but every bearing contained a fire blanket. Every bearing contained a sprinkler system around the perimeter of the bearing. And every bearing had fireproofing applied to the capital above and below the bearing. The capitals themselves were also sized to provide a 400 millimeter zone on all sides of the bearings to enable jacking and bearing replacement should it be needed. And you'll see here that there's a beam grillage above and below the bearings to resist P delta demands. You won't see bearings located on top of cantilevered columns in Chile, as it's not a permitted system. So the good performance of the military hospital in the 2010 Mole earthquake kind of led Chile to require that all new state hospitals be base isolated thereafter. And that led to a sort of standardized design and specification for isolated structures. And that generally consists of the following. So a superstructure designed for the 475 year, which is the design basis event. And it's typically comprises of a concrete moment frame with an 8 by 8 meter grid and a 4.9 meter floor height. That was fairly standard. The superstructure is generally designed for an R of 1, which is an ASE 7 strength-based design. So it's essentially an elastic responding structure. Detailed to ACI 318 to special moment frame or intermediate moment frame detailing requirements. And typically drift limits are targeting 0.2 to 0.3%. And uncracked behavior is typically assumed. And typically the concrete moment frame will be designed using modal response spectrum analysis. The isolated system is designed for a 975 year event which represents the maximum considered event in Chile. Isolated displacements typically 250 to 300 millimeters were fairly standard, and a 400 millimeter moat was also fairly standard. As I mentioned, beam grillage above and below the bearings, cantilever columns not permitted, and the isolation system is typically located at ground floor. This isolation plane is either floating over the ground floor or running into the side of a basement wall. And non-linear response history is typically used to verify bearing displacements and to tune the isolators, which is often using spectrally matched records. So typical isolated structure often comprised of 1 to 2 levels of basement below the isolation, 3 to 4 levels of podium, and then a further 4 to 6 levels of tower over top of that. The second building I'll speak to is the Félix Bulnes Hospital located in Santiago. This was a really interesting building, 11 stories above ground, 3 basement levels, total floor area of 130,000 square meters, so a fairly sizable hospital by any means. Site's located in Zone 2, as Quincy mentioned, which is an intermediate seismic zone, located on a relatively soft site, soil type D. And in fact, the site's actually located over a volcanic ash layer with a 2-second natural period. So the building is situated on 264 high damp rubber elastomeric bearings plus 50 friction sliders. At the time of the design, which is 2012, high damp rubber bearings were actually still permitted, which is why this building contains those. The concrete moment frame superstructure includes 94 fluid viscous dampers located on throughout all three of those tower wings, supplied by Nuentech. So the height of this particular building was such that it just tipped it above the limit in which drifts could be controlled to acceptable limits of the 0.2 to 0.3%. The dampers had a capacity of about 1,500 kilonewtons, 20 millimeter stroke, and came in at a cost of $60,000 per damper, so a total of $6 million for dampers alone in this building. So as I mentioned, the superstructure comprises of concrete moment frames, special moment frame detailing, again detailed to ACI 318, and again designed for an R of 1, so essentially an elastic response. 475 drifts, again less than the 0.3% target with dampers. Interestingly, the dampers, without the dampers, the drift demands are approaching 0.4%. So which didn't meet the Ministry of Health's requirements and hence the need for additional damping. So there's a fairly significant cost to achieve a relatively minor reduction in drift demand, one might argue. So the isolation system was designed to achieve a 300 millimeter bearing displacement, again a 400 millimeter moat clearance. As I mentioned, that was fairly typical and comprised of 4 different types of elastomeric bearings and 3 different types of sliders. And again, non-linear response history was used to tune the layout and again using spectrally matched records. The floor plate of this particular hospital was, and many of the hospitals we visited, was huge. So large, in fact, that these bearings, the bearing design incorporates lateral displacements associated with concrete shrinkage of the ground floor slab. So this isolation design included an additional 70 millimeters of displacement to account for concrete shrinkage, which was quite clearly visible as we walked beneath the isolation plane. You can see here there's a permanent offset of the upper capital relative to the lower capital. With that in mind, I'll pass it over to Ericsson.
Fantastic, thank you, Dion. Let me get my slide. Oops, there you go. So I will talk about Sotero del Río, which is the largest hospital in Chile, or will be the largest hospital in Chile. It has a total floor area of 215,000 square meters, and it will be able to serve 1.8 million people when finished. The construction started in 2022 and is estimated to be finished by 2027 with an expected cost of roughly $250 million US. It is important to note that this cost doesn't account for any type of medical equipment or the computers necessary to run the hospital. In the picture below, the big building labeled ABC, it's 240 meters long and 96 meters wide, and the smaller building labeled D is 96 meters long and 72 meters wide. Both buildings have 2 basements and 5 podium levels, and the building ABC has 5 stories over the podium level. As it is common in Chile, the construction is cast in place, and in this case, the isolators were placed in between the first and second basement with a moat in front of the first basement. The superstructure is composed of intermediate moment frames in 2 directions designed to ACI 318, And the substructure is supported on shallow foundations, which has a design bearing strength of the soil of about 780 kPa for the static case and around 1,200 kPa for the seismic case. In particular, the tender process included both the design and construction of the building, and it had a structural pre-design. However, this pre-design was for different conditions, as we will see in the next slide, and it was not peer-reviewed. So the details were not that good as a starting point. The other issue is that normally the structural designer is engaged post-tender, which means that designer receives this pre-design and it has to use it as a starting point. Slide. So in this case, the original pre-design considered that all the buildings were separated. Every single one that has a label from A1 to D was a separate building with seismic gaps in between them. This was not good enough because normally what Chileans do is they try to target a fixed base period of 1.5 seconds. So with the isolators, it will be pushed to roughly 3.5 or above 3.5 seconds. And then having all interstory drifts less than 0.2% use uncracked inertia. In order to achieve that, they needed to combine all the A, B, and C buildings into just one big massive building, and also increase the size of the columns from initially 80 by 80 centimeters to 90 by 90 centimeters, and even a meter by a meter. Also increase the beam sizes and the concrete strength. With that geometry in mind, the isolator distributions, the objective of the distribution of the isolators was to reduce the torsional response because of the mass of the building, because of the towers was leaning towards the up of the to the north, say on the page. They needed to use more rigid isolators in the top part rather than in the bottom, and this is shown by the red and blue isolators. The red isolators has a cross-section diameter of 1.1 meters, while the blue ones had a cross-section diameter of 890 millimeters. In order to provide damping, only type 2 bearing had a lead core, and in total, for the two buildings, they used 533 bearings. The design of the isolators is normally done with 7 pairs of ground motion records. They do that because they can use the average instead of the peak to size the isolators. And the hazard was studied using PSHA, which was close to 80% of what's a hazard required by the Chilean seismic isolation standard, NCH 2745. However, in the case of this building, it was decided that it was going to be isolated for the hazard that is described in the standard. Another thing that Chileans normally do is they use spectral matching. And the way they scale the records is that the average of the SRSS combination of both directional spectrum is matched to 1.17 times the hazard that they want to build to. For the seismic gap, one of the considerations that is not in the standard but is part of the Ministry of Health requirements is that the probability of impact at a DBE event has to be less than 1%, while at the MCE event has to be less than 10%. So because it is considered that every record is equally probable and that they distribute with a log normal distribution, what they do is they plot all the maximum response of each one of the ground motions, and then they adjust a log normal distribution for the cumulative probability. And that's when they see, someone is changing the slides, not me. Sorry. There you go. What I was saying, oh yes. So for example, for the case of the ABC building, the large one, and for the MCE and 10% probability, they measure from that curve that they require something like 340 millimeters of gap space, but they normally leave, they allow a nominal gap that is larger than that. So in this case, the mode was 40 centimeters along in the perimeter of the building and 80 centimeters as a seismic gap between the two buildings. In terms of the design of the superstructure and substructure, what they normally do is they work as with a linear elastic model, as Dion was saying, but this model is adjusted to represent the DBE displacement and damping. And then the model response spectrum analysis is used instead of the nonlinear time history analysis or the average of those, because they say that it's faster to run the models and also obtain the amounts. As we can see, the acceleration spectra is modified to account for the isolation system. And in this case, the building ABC, the big one, had a translational period of around 3.8 seconds and a rotational period of about 3.3, while the smaller one, the translational periods were around 3.6 and the torsional was about 3.1. From the table on the right, we can see, as Dion was saying, that normally they design for structures that essentially respond elastically, as shown by this air effective here. One another interesting requirement from the Ministry of Health is that the isolators there should be the possibility to replace the isolators. So in order to do that, the designer developed a procedure and account for the demands arising from the jacking operations. The procedure comprises lifting 5 millimeters the capital that wants to be replaced and 2.5 millimeters all the remaining of the column capitals around it. This allows the decompression of the bearing and the removal of the bearing and installation of a new one. For this particular building, the designer accounted for the jacks to be placed on top of the beams as close as possible to the column capitals. And another interesting fact is that I thought originally it was 4 jacks, but if you use 4 jacks, it's difficult to remove the bearing. So what they do is normally they design for the use of only 2 jacks. And finally, the stairs and lifts were hanged from the superstructure, so they were actually part of the isolated system. They used, for both cases, CDF as the lateral load resisting system for these elements hanging. And you can see that in the picture there, it seems to be a wall, but you may remember that I said that this was a moment frame building. Well, this wall is actually not continuous, and the designers allow for some type for movement in the construction joints, so the walls do not interact with the moment frames. So with this, I pass on to Jeff.
Thank you, Erickson. So after visiting the hospitals in Santiago, we traveled up to Iquique, which is a couple of 100 kilometers south of the Peruvian border. So it's located in the Atacama Desert. And what you can see there is the Iquique township. It's a port city that's actually down on the coast. And then immediately inland from that, there's actually a 600-meter high plateau. And Alto Hospicio is actually located up on that plateau. And in that left-hand image there, within the red circle, you can see the location of the actual hospital, and then where that sits within the broader picture of Chile. So, base emergency hospital in Alto Hospicio had both an inpatient and outpatient service, had a capacity of 235 beds, 7 operating theatres, 3 integrated delivery rooms, dialysis stations, and other medical support. Overall cost was about 110 million US, or about 190 million New Zealand dollars. It was 48,000 square meters, 4 floors, and an emergency helipad. And this hospital serves a population of about 375,000 between Iquique and Alto Hospicio. So it is much smaller than the other hospitals we visited, but it's still a really interesting learnings from this. So the Atacama Desert and the location around Alto Hospicio is extremely inhospitable. The Atacama Desert is the driest non-polar desert in the world. The surrounding landscape appears almost completely devoid of any plant life, and it is an extremely challenging location for the design of cladding and longevity of plant, because there is a very high salt content within the soil there. So this is a view actually from the roof of the hospital, and you can see the sort of lack of plant life or vegetation around the hospital, essentially between a combination, I guess, of the high salt content and the very low rainfall that's not particularly conducive to to a thriving plant life. But it's also that there is a real, because of that same high salt content, there is a real challenge from a geotechnical standpoint for construction, and that any water leaks or runoff can actually dissolve the salts and lead to sinkholes. So the foundations for the isolation system here are actually designed for a 50% loss of support, so that if there is any localized subsidence of the soil as a result of these factors, that the design is designed from the outset to accommodate those. Now this here is actually a close-up of that view. This is actually some of the excavations from construction here, and it looks almost like rocks or something there, but that's actually some of the salt that's been extracted from the soil, just to give a perspective on just how challenging those geotechnical conditions are at this location. So these were very low profile friction pendulum bearings, just at the isolation layer of the hospital here. And what was actually done here was a partial height floor, so it wasn't actually considered a habitable floor. So there was restrictions on use, restrictions on any sort of plant or anything that could be put in there. But with that, it meant that there wasn't the same requirement for the passive and active fire. So Dion talked earlier about the extent of the passive and active fire that was evident in the military hospital. But because of this condition, that wasn't the same requirement for this hospital. So that was ultimately, I guess, deemed as a favourable choice on balance. So this is a view of the isolation plane with the partial height floor and the isolation plane. One small detail that we saw was that some of the bearings had still had their transport bolts were installed. So this was something where they had a transportation bolt just to stop the bearing moving in transit, and some of the bearings hadn't had those removed as planned. So there were some, during a low-level earthquake, there had been some of those sheared off, and it could potentially have a small impact on the level of base shear for sliding for a serviceability limit state earthquake, and not going to be necessarily a huge issue, but could potentially have an adverse impact on the performance and longevity of the bearings if that's in the interface. So that's just a view of one of the bolts, transport bolts that had been sheared in one of the prior earthquakes. So for overall the moat detailing and the accommodation of relative motion across that isolation plane and between the superstructure and the surrounding ground was actually really well done. There was good detailing in terms of suspension of services and cladding. Moat covers were really well detailed, and the gaskets in key locations at that moat clearance, and also restriction to locations which otherwise might be a pinch point during relative motion between that structure and the surrounding equipment. That said, there were a few small issues that had arisen. The designer for this hospital had actually travelled with us, and when we visited the hospital, it was very early in its operation, and we visited the hemodialysis unit that was still being commissioned, so it was very early on, and there were a few small details that were picked up. The designer was a bit alarmed to see some of these things, and was then embarking on a remediation program to get some of these details corrected. So certainly no criticism of the design. It's just with that many people involved in the building with this much plant, and the odd thing can go wrong. So in this case, there was some plant installed on top of the moat covers and between the moat cover and the surrounding ground. So this is a different view of that same location. There's just different plant that's been installed partially onto the moat cover and partially onto the surrounding ground. So while that probably won't stop the building moving, there may be some adverse impacts in this region prior to the remediation works being done. The other thing, again, good detailing here, in that the traffic island is discontinuous between the superstructure and the surrounding ground, but at the same time, the moat cover there, as the building displaces and the moat cover is intended to lift, actually won't have anywhere to go just because of the location of that traffic island. So, clearly good intention here, but some slight issues with the detailing. And then also in a couple of slides ago, there was a lot of pallets stacked up on the moat cover at one point. In this case, there's some boxes and things stacked up there. So again, not a massive issue, but it's something where it's probably a challenge in all buildings like this. To the average building user doesn't appreciate the desire to not necessarily have too much equipment or things stored in that location. This was actually up on the roof. This is just sort of dust and yeah, some slight corrosion already on the plant. It is an extremely challenging environment for this to operate. This was not actually any relative motion from the isolation. This was a pipeline which existed entirely on the roof. There seemed to be a bit of disagreement within different consultants whether this type of detailing is actually needed. But this was sort of, we believe, a combination of possibly movement through inertial forces during shaking or just accommodation of thermal expansion and contraction. So quite a good detail, potentially not necessarily needed, but yeah, well detailed overall. So with that, I'll pass across to Mark.
Thanks, Jeff. I'll start with speaking about the Provincia Cordillera Hospital, which we visited on the afternoon of the Tuesday that we were there. It's a hospital that's about 100,000 square meters, so pretty big building. It's got about 200 base isolators under it, and above the base isolation plane, it's got a special moment frame. The special moment frame, as Dion kind of alluded to, is stipulated by the Ministry of Health over there. So they decided that they wanted to have that detailed to the ACI 318 special moment, even though the designer admitted that the structure was actually going to be elastic at the design level event. What was quite interesting about this hospital is being built by the same contractor as a couple of other hospitals in Santiago, and what this contractor was doing, which I thought was really good, was they were prefabbing a lot of the items that could be prefab. So they were prefabricating the bathrooms, which is relatively commonly done around the world. The facade elements, you can kind of see in the top right, some of those facade elements were prefabricated and brought to site and installed. What I thought was relatively novel was the bed heads, where you have a lot of medical gases and electrical components all coming into a relatively tight environment. The contractor had decided that they were going to prefabricate those offsite to stop the subcontractors from sort of crawling all over each other to install those elements. They saw it as a really good opportunity to improve the quality and ensure that they got that part of the design nailed. On the Monday, we visited the Baha'i Temple, which is up against the mountains in Santiago. Absolutely beautiful structure. If you go to Santiago, I'd definitely encourage you to go and visit. The construction for this building was finished in 2016. It's got 9 petals, so you can kind of see the structure that goes around the outside. On the outside of those petals is cast glass, and on the inside is translucent marble. So it has this amazing effect when you're inside of light coming in, and yeah, really cool structure. It's about 30 meters wide and about 30 meters high, and sits atop the relevance to our trip. Not only it's a beautiful building, but also it's base isolated. So it's got a concrete disc at the base and sitting over the top of base isolators. So cross section of how that kind of works. So you've got a column in the middle, and then you had under each of the 9 petals of the surrounding superstructure, you had a column that supported that, and that column that was then supported by the isolators in that location. And then on the right-hand side is that sort of space truss supporting those facade petals. That was pretty amazing to have a look at. Very complicated to try and achieve, that you've got brittle cladding materials whilst accommodating motion, and then trying to get all that constructed. There were some really cool details as to how they achieved that. And then central image just around shows some of the challenges that you have with entrances and landscaping around the moats of these buildings. So how you cantilever out those structures and sort of achieve the entrance requirements for people visiting the building whilst making sure that you have that isolated. So I was tasked with commenting on some of the good and could be done better items that we saw along the way. We talked a little bit about the military hospital, which we visited on the first day. They had some really good resilience planning that they had worked through. So they gave us some examples of these generators. So they had 6 generators that they could operate relatively easy on 50% power, and had even prioritized down to which power plugs in the building would be operated at that 50% power. So they prioritized monitors that the nurses and the doctors needed to use over other things that were sort of not as required. So they could go for a whole week at that 50% power with the amount of diesel and the generators that they had on site. Another cool aspect of the hospitals that some of the ones that we visited, is they seismically monitor a lot of the hospitals. So that's going to provide some pretty awesome data in the future, given the frequency of earthquakes that Chile experience and also the number of base isolated hospitals. I think there's going to be some really awesome information come out of future events. And some really good examples of the non-structural elements or services crossing the isolation plane, where they grabbed hold of the service before it crossed the isolation plane, put on a flexible hose, and then grabbed hold of it on the other side. So we saw some really good examples of that in action. They'd thought about, in a lot of the hospitals, how they were going to protect important plant that they needed to use and restrain it. So you got the image of the tank, just got a nice frame holding it down to the floor. And they'd thought about a lot of this. Dion sort of covered it, but trying to protect those potential vulnerabilities in the structure. So they had this fire rating, active and fire protection around the base isolators in these car parks to really protect those things that they saw were potential vulnerabilities. And then the other image of, they'd put in a lot of the gravity restraints for holding a lot of the pipe work up, and then they came back with a relatively easy to install sort of upside down portal to provide the seismic restraints to some of the services in there. So nice, simple, repeatable way to achieve that seismic restraint of those elements. Some things that we saw that could have been done better. We did see examples where services that were crossing the isolation plane, that they'd thought about putting the flexible hoses in and things, but the temptation of restraining or grabbing hold of it before it crossed the actual plane was sometimes not quite right. Jeff sort of covered a bit of the durability at the exposed Alto Hospicio location was really difficult. You're getting some pipe work that is exposed and already starting to show some signs of rust due to the highly corrosive environment in those sort of regions. And then the ductwork, that we didn't see too many seismic restraints done on ductwork, and it could be that they not so worried about ductwork, but that ductwork could become a hazard to either a ceiling or people underneath it in an earthquake. So that was sort of inconsistently applied around the locations that we saw. And then just some more examples of where the flexible hoses have been put in, but in an actual event, the top part of the isolated structure could potentially bulldoze into these pipes and cause them to fail. So flexible hose, but just making sure that everyone understands where that needs to be located and how it needs to operate, so that the structure can move freely and the service that you're trying to protect isn't caught in between. And then another example on the right of a similar sort of theme of just making sure that the location where you go from a solid service to a flexible service is really located well and thought through. And with that, I'll pass you over to Jan.
Sorry, Jan, I don't think we hear you. Or it's just me.
No, not just you.
Can you hear me?
No.
Can you hear me?
Still
No, I
no.
don't think. So for everyone to know, we tried this earlier and it was working perfectly fine.
In the meantime, it's probably good to mention if anyone got any question, they can type them in the question and answer box. We've seen one already, and at the end of the session, if we have any time, we'll try to answer them live.
Can you hear me now?
Much better.
Yes.
Yeah, you don't know what went wrong there. Just kept clicking the same button. Right. Sorry, team. I was tasked with sort of talking, rather than any particular building, more sort of the general resilience and some other observations. So as mentioned by others in particular, resilience was a really big focus for the hospitals that we went to. We went to, obviously more recently, constructed and hospitals in construction. And as Mark mentioned, a prime example of that was the military hospital, where they put backup generators, but in fact they had backup with the backup generators, where they only needed actually 3 generators to run at 50% power rather than the full 6. In terms of overall resilience, the Ministry of Health in Chile invests their money in new resilient hospitals. So we asked the question about seismic strengthening, and they don't do seismic strengthening. Rather, they spend their money on new infrastructure, and they do it really resiliently. Another aspect of that, when thinking about it more holistically, is you'll remember that Quincy said that there were 39 hospitals in Santiago. And interestingly, 60% of the population of Chile actually resides in Santiago. So by having 39 hospitals with 60% of your population, inherently, you have resilience there as well. So, and just in general, you may have been interested in some of the photographs that have been coming up and the shapes of the hospitals. Well, Chile have a requirement that all hospital wards must face north. And that means that service areas are on the southern side. And the implications for that is that you end up having skinny structures, finger-like structures, depending on the shape of the site, or long, skinny, sitting on a podium. And you may remember some of the photographs that the team have been showing. As Dion mentioned, all critical services since the 2010 earthquake, including your ICUs, your theatres, your medical equipment, must be in base isolated buildings. They do allow for industrial services, your ward buildings, to be in non-base isolated buildings. But what that means is you may actually have in those situations, and we saw a few hospitals where this occurred, where you've got your services coming across, your fire sprinkler pipework, your medical gases and other services actually crossing the isolation plane. Some interesting observations around how they do construction observation in Chile is that all hospital projects have an independent, full-time, on-site clerk of works. They're called an ITO. Now, the clerk of works is not engaged by the designer, and they're not engaged by the contractor. They are independent. And the clerk of works is responsible to ensure that the design is implemented as per the construction documentation. And the clerk of works engages as many engineers and experienced people with expertise to observe all aspects of construction. But ultimately, the responsibility for sign-off at the end of the project that the project has been built in accordance with the construction documentation sits with the clerk of works. So the clerk of works will consult with the designer if there are questions on the documentation, or if there are things that have come up on site. One of the hospitals that we went to had some issues with the seismic installation and coordination of non-structural elements. But when we dived into it a little bit further, we found that the key issue was actually that the non-structural element seismic design had not been incorporated in the structural engineer's design scope. And when the clerk of works was doing the checking, they were only checking what was on the documentation, and there was a scope gap. But what we observed is that scope gap has actually appears to have been resolved on all of the hospitals that are currently under construction, and they have the non-structural seismic design as part of the structural engineer's scopes. So in terms of the seismic design of non-structural elements, as mentioned by Quincy and Dion, is that non-structural element damage in the 2010 Morlaix earthquake impacted many of their hospitals, and many of the hospitals were out of operations due to non-structural damage. So it really put a focus from the Ministry of Health on the seismic performance of non-structural elements. Since 2010, there's been a requirement for the seismic performance and the seismic design of non-structural elements to be considered. And as we were talking to the teams, they've had very similar issues to New Zealand in changing the way of actually designing for the seismic, because they're saying that the contractors really wanted to install and do their designs for their non-structural elements as they've always done. And that has been a challenge, but they did say that they're definitely seeing now significant improvements as the contractors are getting more used to doing the seismic design and installation of non-structural. As Dion mentioned, they've got a standardized grid for all hospitals, 8 by 8 by 4.9, and that 4.9 floor to floor height really gives them a lot more space, or good space in the ceiling void. In the Félix Bulnes hospital here on the right, what we saw was that they put the majority of the in-service ceilings going down that corridor up. They had the gravity hangers in place, and they still needed to come back and put the seismic restraints in. There was going to be a little bit of congestion to get it in, but they were aware of it. But they are noticing that at the moment, they're still often got individual sub-trades coming in and doing their own install of their services, and that overall coordination isn't currently being done by the contractors, but they're saying that the contractors, as they're going through more and more hospitals, are understanding that that's the way to go in the future. So in summary, Chile has very established structural form, layout, design and construction monitoring processes for new hospital buildings. And those things really support good seismic performance outcomes. And whilst New Zealand and Chile use different structural design philosophies, and we have different seismic design requirements, both countries end up with high-performing hospital buildings. So in terms of this project, there's certainly more for us all to learn from each other, from both Chile and New Zealand. There's continued opportunities for us to exchange ideas and learn from our experiences, and to calibrate our risk settings, and certainly around hospital design philosophies. And in particular, we've got a couple of things which are currently or about to occur in terms of next steps. And the first thing is a side-by-side design comparison. So what's happening here is that we're both in New Zealand and in Chile, we've got a preliminary hospital design exercise going on. We'll be using the same floor area and medical function. The location is using the same seismic hazard spectra. So we've chosen Santiago and Whakatane. You'll see the spectra down the bottom right. The design of the primary structure and the base isolation will use the codes and the hospital-specific requirements for each country. And then once that preliminary design is done, we're going to compare the performance at SLS2, 1 in 500 years, and then ULS and MCE. We're also going to have a look at high level at the seismic performance of non-structural elements by having a look at the drifts and accelerations on each floor at the SLS2, 1 in 500 year earthquake. The idea is that we're going to compare the processes and the product that it leads to, and that the New Zealand model that's being undertaken will be published as a worked example, which is following the NZ-Chile base isolation guidelines. And the second item that's occurring is instrumenting a base isolated hospital in Chile. So there's been funding approved to instrument a major base isolated hospital in Chile with a 10 sensor array. And obviously that's going to be done in conjunction with our Chilean partners. And the data from that instrumentation will be made available to the wider public for research purposes. And the funding and instrumentation is to commence in March 2026. But just a note there from Quincy that collaboration, extension, and ideas are all welcome. So please get in touch with Quincy if you have anything that you'd like to add to there. I'm going to hand over to Quincy now for if there's any questions.
Right, so I think we conveniently all spoke on time and leave ourselves about 5 minutes for any questions. So feel free to type in more questions into the Q&A panel. In the meantime, I think I will raise the question here by Chris to sort of the general audience here. Any general comments on Chile's approach to base isolation design versus New Zealand? Based on draft New Zealand guidelines, New Zealand hospital was designed for MCE, or 1 in 10,000 years, versus Chile's 1 in 1,000 years, versus US 1 in 2,500 years. Shouldn't we consider this approach allow for more affordable implementation of this highly resilient system? So I'm going to refer it to Dion to tell us his answer.
Yeah, one of the things that really fascinated us is that Chile's hazard was just so well suited to isolation. Their hazard is very much informed by their historic earthquakes. And so they've essentially got a peak ground displacement of sort of circa 400 millimeters at a corner period of about 3 seconds, I believe. So it's very easy to make an isolated system work. In comparison to New Zealand, where a hazard is informed by seismic hazard models, we've got very large displacements to contend with. So yeah, it was a common topic of conversation around whether we need to change, whether there's room to change our approach in New Zealand. Whether that happens or not, I'll kind of leave it there, but it was a big eye opener.
Yeah, I might just sort of add to it as well. I think this is where, the role of seismic instrumentation could help in the future. It's always good to have these, seismic hazard model, but then I guess the approach that Chile has taken is that, through actual measured, performance, they weren't really getting any ground motion that was able to generate those very large displacement coming from, these really long return period. So, maybe as we instrument more buildings, we could collect sort of greater body of evidence so we can proceed with more confidence in how we calibrate our future design codes for base isolated structures. So, waiting for a few questions. So maybe while we're waiting, we'll also have an opportunity to talk to the first question that was posted there. It was a question from Fabrice. So it was mentioned that 70 millimeter displacement due to shrinkage for the second hospital is quite significant. Do we know what was the distance between adjacent expansion joint? And I think at this stage, I'll open it to the full panel if anyone could remember any details regarding about this shrinkage issue. If not, then I'll probably just jump in. This was one of sort of the area that was particularly eye-opening for us. As we haven't really have constructed as many base isolated hospital as Chile is, we really haven't come across as many of these interesting practical issue in design and construction. So it was really good to really pick up these details. And at the same time, I think Erison's got a more considered answer. I'm going to pass it on to him. No.
Oh, sorry, Quincy, it was for me.
Oh no, it's fine. I thought you tried to sort of give an answer to the shrinkage issues.
No, I was looking though at the Ministry of Health requirement, and for the shrinkage, there is a specific requirement that says that that designer has to consider an initial displacement of the isolator of 50 millimeters. That is a part of our requirement from the Ministry of Health. So I suppose that I don't remember either what's the distance between cast strips, but probably is enough to generate an initial displacement of 50 millimeters for normal size buildings.
Right. Okay, so we've got we've got a question coming in. According to New Zealand practice, drift checks for base isolated structures are done using gross or crack stiffness for concrete elements. I'll refer that question to Dion and Ericsson, if you guys like to chime in.
Yeah, it did take us by surprise a bit that all of their drift assessments are based on gross properties, which even if we were designing for an elastic structure, we would probably account for cracking over here in New Zealand. But that said, they their design is well tried and tested. So it's essentially they've managed to convince themselves that's the appropriate way to be designing and evaluating the drift demand. So yeah, and it was another common discussion or talking point, but that's how it's done.
Yeah, I guess in the next phase of our project where we're doing the comparison study, we would be able to interrogate more into that assumption and see sort of the effects of it translator and design in our two phases. So I've got another question here. For the hospital that Ericsson presented, I believe that's the Sotero del Río, the R factor was assumed equal to 1.23 for the superstructure under DBE earthquake, which show the structure is sort of flexible. Since the soil category was D, and regarding the long period of superstructure, how the resonant effects was checked for this hospital, Ericsson?
Yep, no, that's actually it's a mix between two hospitals. So I presented Sotero del Río, which has an R factor of roughly 1.23, the effective one. I'm trying to find that. So here, but it was not on soil category D. That building was actually Félix Bulnes, which is a different building. I don't have an answer for the question on how the resonance effect was checked for the hospital, but what I can say is that the 1.23, it was for a different hospital in a different soil site.
Yeah, if I remember correctly, the Félix Bulnes hospital being located on soil type D, I think the fact that it was located over volcanic ash, if I remember correctly, I don't think that was actually fully understood at the time of design, so it was a relatively new piece of information. But yeah, suffice to say, it was designed for a soft site, but just not the recognition of the volcanic ash below it.
So I've got another, probably going to be the last question of this session. A really good question. In the NZ-Chile base isolation guideline, there is no specific requirement to make sure the adequacy of non-structural adequacy. What is your advice in this regard? I think maybe I'll pass it on this question to Jan and Mark at the beginning.
So the question, Quincy, was around the base isolation guidelines not having any requirements or considerations for non-structural.
Yes. What's your advice in that regard?
Certainly when it comes to having a look at your floor accelerations and your drifts, it's still really essential that whilst the base isolation guidelines are for the design of the isolation and the primary structure, when you're doing the non-linear time histories, you still really need to get what your accelerations and drifts are in your superstructure, and then having a look, for example, at the code of practice to be able to then say, well, how's my building going to respond? Because that 1 in 500 year finality is just so important. I'm not sure if that's helpful. Anything to add there, Mark?
Yeah, I think the focus of that guideline, to my knowledge, is the base isolated aspect of the structure, but yeah, the non-structural, you can definitely we've done it quite a bit where you take advantage of the base isolation effect on lowering your accelerations, which can be really effective. But yeah, the making sure that when you go across those isolation planes, I know has been well thought out, or it's a pretty important aspect to make sure you really nail that in design. But the rest of it, designing services seismic for reticulated surfaces and your ceilings and your petitions, you can definitely take advantage of lower accelerations, but I wouldn't see it being necessarily any different. You just can take advantage of that effect.
Yeah, and I think, when designing for hospital, there are other documents that are overarching that that you might need to refer to. So, for example, like the Ministry of Health has their own sort of structural and non-structural guidelines that you need to make sure that your design is compliant with too. Those other documents might prescribe requirements that are beyond, the guidance process between the NZ-Chile base isolation guidelines process. Absolutely last question, especially because it's coming from Ian. Is peer review a standard part of the design review approval process for isolated hospital? Should be a simple one for anyone to jump in.
Yeah, I can jump in there. Yes, it is. Sorry. I had it on one of my slides and took it off, so apologies for that, Ian. But absolutely, yeah, peer review is a requirement, independent peer review, as well as the independent construction monitoring.
Cool. Now I'll pass it back to Catalina to close the webinar.
Well, thank you very much, everyone, for an amazing presentation. There's definitely a lot knowledge to exchange, a lot to learn from each other. So this was amazing. Just want to keep it short. Thanks again, and stay tuned for upcoming seminars for next week and following week. So probably NZ members are going to get an email about the upcoming seminars. And that's it from us.